We did a multiplication. It's only natural. Got to do a division, right? Okay, so here's two new functions, this guy and this guy. And it's asking you just to straight out divide them. Yeah, no problem. All right, so let's take f of x, which is x plus 2. Let's put this over g of x, which is x squared plus 9x plus 14. Now, this always worries me whenever I see a trinomial like this because I'm just wondering, can we factor this? Well, probably, yeah, we probably can. So let's put the x plus 2 up here all by its lonesome. That's nice. And do a quick factor of this. Oh, you should be able to do this in your head by now, right? Two numbers that multiply to give me 14, add up to 9, 7 and 2, of course. Now, check this out. This is really, really quite cool. What's going to happen is these x plus 2's are going to end up canceling out to leave us a resulting function of 1 over x plus 7. But if you remember your math 20-1, you have to include both the non-permissible values here. In other words, you've got to tell me what are the NPVs before canceling. And you can figure that one out in your head. That's going to be x cannot equal to minus 7. And you can figure that one out in your head, and x cannot equal to minus 2. But some really interesting stuff happens when you start graphing these guys on your grid. Now, I'm not going to do too much here because that's actually going to be part of the rationals unit, which is coming up soon. But I'm going to show you some really, really, really cool stuff. Okay, so let's graph a few things here and let's go from there. First things first, let's graph this guy in green here. X plus 2, real simple. There's 2 right there. Rise of 1, run of 1 gives you there. Rise of 1, run of 1. Look at this. Rise of 1, run of 1. This is all the slope of rise of 1, run of 1 right there. So you can draw a real pretty line going all the way through here. And as a matter of fact, you can even go down 1 over 1, down 1 over 1. Look, this is going to give you a beautiful, beautiful resulting line here. So I'm going to take this guy. I'm going to do a line, right? Yeah, perfect. In green. Let's choose that color. Sure, why not? And I'm just going to extend this. Now, remember, when you do graphs like this, make sure to extend that graph beyond the grid. Either that or put arrows on it, okay? When you extend beyond the grid like this, that means that that graph is continuous and will go on forever and ever. Amen. Now, let's do this guy. Remember, it's a parabola. Well, wait a second. If it's a parabola, it's going to have, guess what? Yep, x-intercepts at minus 7 and minus 2. So minus 7 and minus 2 are right here. Interesting. And somewhere in the middle of that, of course, is going to be your vertex. You also know that this is going to have a y-intercept of 14. So maybe at this point, it might be advantageous to actually throw those values in and find out how low does the vertex go and a few other things like that. So, okay, hold on. So I got my calculator up here. I'm just going to put in our original equations. That was x plus 2. And the other one, of course, which was x squared. Where are you? X squared, there it is, plus 9x plus 14. Okay, so let's just graph this. Let's see what it looks like. Here we go. There's that line. Oh, exactly as we predicted. Holy smokes. My curiosity, though, is killing me. I want to know, what is that vertex way the heck down there? Remember how to get that? Second calc, find the minimum. You got it. Left bound, right bound. Here we go. But we're on the wrong graph. So move your arrow up or down to change equations. Okay, there we go. We're on the right graph now. So here we go. Left bound, enter. Right bound, enter. Guess, of course. And it's minus 4.499999 minus 5. Minus 5 minus 6.25. That's the value down there. Okay, so let's put this over here on a graph. So minus 4.5, right? Was that the value? Wait, let's do it again. Minus 4.5, there it is, minus 4.5, okay? 4.5, which is about there, all the way down to about 6.25 right down there. So our graph kind of looks semi-accurate, looking an awful lot like that. Holy smokes. Now, how are we going to get h of x out of this mess? Well, here's something that you got to remember from Math 20. Math 20, a graph like that just gave us bendies. And remember, it gives us a nice little asymptote here at, guess what? The non-permissible value. So we can actually just go over and just do it right now. There it is, right? And now, what I would do at this point, just to make sure everything is accurate, go back to your calculator, okay? I'm going to clear everything off here. In my y equals 2, I'm going to keep the equations here. I'm just going to hit enter. So the equations are still there. They're just not going to be graphed. And now I'm going to put my y1 divided by y2. Okay, so alpha, calculate. Here we go. y1 divided by alpha, f4. There it is. y2. Okay, now watch what happens. It's only going to graph this. And yep, there it is. And there, of course, is your asymptote. Beautiful. Now, one thing I want to show you, though, which is really, really, really cool. Do you remember that value here that we canceled out at x plus 2? And I said that's a non-permissible value at minus 2. My question is, look at this graph. Look at this graph. Why isn't there an asymptote at minus 2? One of the reasons why, and this is something you're going to learn a little later on, so I'm not going to go into too deep right now. Because it canceled out, it doesn't make you an asymptote. It actually makes something that's really interesting. Now, you're probably asking yourself, is that minus 2 allowed now because it's canceled out? No, actually, look, this is going to create what we call a hole in the graph. How do I prove that the hole is there? Real simple. Watch. Let's go to the table. Okay, there's minus 2. Look, there's the error. There's the original guy that was canceled out, still coming back to haunt you. And that's one of the reasons why we always have to make sure that we include that non-permissible value before we cancel, right? So in other words, how would you draw something like this on your graph? Well, real simple. You know that this guy over here, right? This guy here, comes in this way and goes down like that, bada boom. This guy over here comes down this way, goes towards the 2, right? But right at the 2, there's an error. So we put a little circle saying that's where the error was. That's where our non-permissible value is. There's our hole in the graph. Cool, right? I know, it's awesome. Okay, so we sketch the graphs. There it is. State the domain. Real simple. All values of x such that, remember, x cannot be two things, and that was the minus 7 and the minus 2. So x cannot equal to minus 7 or minus 2. Otherwise, x can be any number at once in the real numbers. Look at the range now. The range is also very cool because if you think about it, look at this. Look at that. Do you remember? It's got a horizontal asymptote. Ha 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 ha. So all the y such that y has to be less than 0 or above 0, but just not 0. Okay, so we'll just say y can't equal to 0, but y can be anyone else. It can be any other kind of number that it wants to be. Wow, what a cool question. You have learned so much. Okay, I need a break.